All right, so we're just going to jump right into the lecture tonight, and we're going to do a little walkthrough, but we're going to talk about SQL and Postgres and just kind of relational databases. So up until this point, all we've been really doing is writing small applications and like using OP, like apple trees, school interface. We just had assessment 2. And we did a little bit of persistence utilizing CSVs, but we're trying to be full stack developers, and you can't really develop an entire full stack web application that's completely scalable using just CSVs to save data or a text file to save data. So we're going to actually need an actual database. And one thing about databases, specifically SQL or relational databases, is that, it seems like every few years there's like the new hot language or the new hot framework. Like when Code Platoon initially started, we were teaching, Ruby on Rails for the back end. So not even Python, we were just teaching Ruby, and then React on the front end. If coding boot camps were 20 years ago, it would have been like Java and jQuery or something like that. Because it seems like every, half decade or decade, there's a new hot language that's very popular. But what's one thing that's nice is that interacting with databases really hasn't changed the past 30, 35, 40 years. SQL, which stands for structured query language, it's changed a little bit, but it's got like little minute different flavors or little add-ons and capabilities, but overall it hasn't changed that much, and it's probably not going to change in the near and or distant future. So that's one thing that you can kind of take comfort in, is like, I learned how to interact with databases using SQL. I'm not going to have to go and learn a totally another language to interact with databases. So there's people that like their whole careers are revolving around SQL. Questions on that? So SQL is a language and how we communicate to a relational database. And what is a relational database? Can anybody tell me?
It's like organized in a certain way. Something has to do with how it's organized, right?
Yes. So what makes it a relational database is how it is organized. So
it's comprised of like, oh, sorry.
No, go ahead.
I say it's made of like different tables, all of which have some sort of unique identifier. So they are queried in a different way, but they are connected at a higher level.
Yep. So as you said, I heard the term tables. So if you think of when we're talking about CSV files, or like reading and writing to a CSV file, you can think of each was a bank accounts. I think it was. There's like accounts, customers, and how you relate those customers to those accounts. If you think of each CSV file as a table, if you want to like visually kind of relate that to what a relational database is. But yeah, you're exactly right. So there's two major types of databases. There's relational databases, which we're going to be working in, and there's non-relational databases, which is something that is where the data isn't connected per se, like a relational database is. So this is an example of Firebase. It's a Google product. It's a non-relational database. This is what it visually looks like from like a UI perspective. And then on the left-hand side is what a relational database kind of would look like. We have tables, so product, order line, customer, order status. Those are considered tables. And each table is connected to each other table via a specific identifying field, such as a product ID. So a product ID on product table also exists on the order line table. So they're connected. So all relational databases kind of look like this. If you think of it as a, like almost like a spreadsheet, columns and rows, and we'll kind of talk about that. What questions do you have about relational databases? And there's a bunch of different types of relational databases. So here we're going to be teaching Postgres, which is a relational database. Postgres is an open source, so it's a very popular relational database, but there's a plethora of other types of relational databases. Microsoft has their own, Amazon has their own type of database. So there's a bunch of relational databases. Like think of them as brands, like a brand of a relational database, but how you communicate with those relational databases are all the same. And that's via pretty much SQL. All right, so there are two halves to relational databases, and RDBMS stands for Relational Database Management Systems. So there's two halves. There's the storage mechanism. That's like how your data is stored in the database. So it's via tables, columns, and rows. And then there's also the querying language of how you actually run queries on to retrieve data or insert data or delete or modify data. And that's through SQL or SQL, which just stands for, again, structured query language. Questions on that? So again, how we actually store the data using tables, columns, and rows, and then how we actually query the database or read, write to that database. All right, so tables, because we're talking about, there's two halves. Talk about the first half, tables. It's actually, so we have tables. So for example, we have a students table that has, so this is the students table, which consists of a bunch of student data. And tables, the name of the tables should always be plural, because the students table holds a collection of students, so plural, a number of students. And then we have a columns. So each column is a specific attribute related to that students table, such as ID, first name, last name, whatever you want. And then there's a record. So each row represents a record of a student. So for example, we have Tiana with an ID of 1, first name Tiana, last name Low, she's on probation, is false. So we have the columns. So we also have column headers. So that represents what type of data belongs in that row or in that column, such as ID has 1, 2, 3, 4. First name, probably a string. Last name is string. On probation, it looks like a Boolean value. So the columns determine what data type goes in that specific column. Questions on tables, rows, columns? What does this look like?
CSV.
CSV file, yeah. So if you just think of a relational database to visually think of what it looks like, think of it as like an Excel CSV file, etc. All right.
Tom, so
Yep.
so when these tables get generated, well, typically what's the file format that gets used?
So today and in the like future, not all of it, but like for the next several days, they're going to be SQL files. So we're not going to be using Python or JavaScript or whatever. We're going to be using SQL. So over the next several days, it's just going to be pure SQL. But in the future, because learning so many languages, so if we're really proficient at Python, maybe we can generate these tables using Python. So that's where we're going to talk about a oh man, I'm drawing a blank on what it's called. Oh my gosh. Essentially, it allows you to write Python that converts it to SQL, and it will create your tables for you. Does anybody know what I'm talking about? I don't know why it's late. An ORM. So you'll hear the term ORM, which stands for Object Relational Mapping. Objects, so you're writing Python objects, and it's mapping over, creating SQL, but we don't need to worry about that now. So for tonight and Saturday, you're going to be writing raw SQL. All right, schema. So a schema is like the architecture of what your database is going to look like. So when you're thinking about like, oh, like what table should I have? What should each table, what kind of data should that table hold? So like, for example, the students, all right, well, what data should go in that students table? Maybe what other data do we need? What other tables do we need? So a database schema is just that the plan, the architecture of how you're going to architect your database. So table names, column name, column types. Like, so when we're creating like that students table, like, all right, what other data do we need in here? So we're going to need first name, last name. We're almost always going to have an ID in there. Maybe there's other data in here that we might need, such as like, grade, like what grade they're in. Did somebody say something? No. All right. So those are some things to think about when you're designing your database schema. And just like when you're trying to solve an algorithm and when you jump right into coding, like that's not the best practice. You should pseudocode first. Just like when you're creating your database, don't just start creating your tables, just coding out your tables. Actually draw what your database is going to look like, similar to like this part. So this is one way you can visually design or your database schema before you even write an ounce of a line of code. And there's plenty of different applications out there to help you design your database schema. And this is just one of them. All right. Questions about database schema design?
Will we be using any of those? I guess it's a tool to draw up schemas.
Yeah, you can use this one, which we'll link it in one of the challenges in the future. But to be perfectly candid, the easiest way I find is grabbing a piece of blank white computer paper or a notebook and literally pen and paper, just draw square boxes and do it that way. That's kind of what I do in the past. That's what I've done in the past. And it's very helpful. Because there's still a little bit of a learning curve to understand how this application works. But it's a lot easier just to draw it on a white pad and paper. All right. I'll also say this about database schema design. It is more difficult than you think. So think of database schema design as trying to solve an algorithm. There is more often than not a right way to do things, and there is a wrong way to design your database. So don't just think, oh, I can create, if I wanted to create Facebook 2.0 or Venmo 2.0, like what tables would I need? Like that, like database schema design is actually more difficult than students generally typically think it is. So they don't spend a whole lot of time on it. And then when they go to develop their application, they pigeonhole themselves by not developing the right database schema for their application. So database schema design is extremely, extremely important. So don't think it's like easy, because it's generally not. All right. So in the database schema, we have tables. So tables are identified by a name. So such as the students table or the addresses table. And right here, this create table, students followed by some other data. This is an actual SQL query. So that's what the actual SQL language looks like. So if I need to create a table, I literally type create table, name of the table, students, and we'll get into what goes in between the parentheses later. So almost any name is valid. These are good naming conventions to follow. Always have them be lowercase, and they should be plural, such as students, because this table holds multiple students, and addresses holds multiple addresses. Excuse me. It's also very good practice to include a unique integer column named ID on every table you create. So just like there's an ID column on every table you'll create, you'll have a ID field. And a lot of these times, it's pretty standard on how you create them. All right. So table names examples. So what does the table store? It stores people, so the table name should be persons. If you're developing an Amazon competitor and customer needs to buy, a bunch of product, you have a purchase order. So it'll be purchase underscore orders. And liking a post, it'll be like. So Facebook or Twitter or Reddit has likes. There might be a like table or an impressions table, something like that. Questions on naming or table naming conventions? All right. So columns. So each column has a name, such as ID, first name, last name, on probation. And they also have a type. So what data type goes in there? So each column has a name. There'll be lowercase, singular nouns, or adjectives are good naming conventions. So for example, in the student table, we have an ID field, and there'll be an integer. We have a first name, which is a varchar, which I think is like varying characters. And so this varchar, it's a characters. So essentially this is a string that goes in the first name. And this field has a max length of 255 characters. So you can't go over that in the database. And you can name this, it could be, you can limit this to only 12 or 254, but if you're using a varchar, it cannot be more than 255. If you need to, if you're doing like a big paragraph that needs more characters than 255, you'll have to use a different type of column type. And then on probation, if you're using a Boolean, a true or false value, you can use a Boolean type. Questions on how to create a table in SQL. And don't worry, we'll go through all this. We'll do a demo of it. All right. So each column type has a type which determines what kind of data goes in. So we kind of just went through this. Varchar is a fancy way of saying a string up to 255 characters long for varchar. And here are some other column types. So we have integer. So, and these are limited in scope because integer field, it can only be that size. Decimal. So if you want to use fractional numbers or floating point numbers, you'd use a decimal data type. Varchar, text field or text, strings as long up to 16 kilobytes. Date. So if you want to use a date type or timestamp, so date with a time. Those are some common ones. There are more, but these are the most common you'll see as far as the column types. So the reason why creating or designing your database schema is so important is because if at any point you have your application, it's created, it's out in production, and all of a sudden you realize, oh crap, I need to make, like I messed up somewhere, I need to add an additional field. So you'd have to modify your database schema. And you can, early on when you're just creating small databases like we are in class, it's easy to just delete your entire database, go ahead and make your changes in your SQL file, and then reload or recreate your database and your database tables and everything. But when you do that, it deletes all the data. So when you are designing, it's very important to try to get it right the first time. But it's never, you'll never always design it, your database schema, to handle all the edge cases as your application scales. So you will have to modify your database at some point. So when you modify your database, you can't just, well, if you're doing it in production code, like an actual application that actual users use and your business relies on, you can't just drop your database and delete all the data and then make your changes. You have to modify your database while there's actual live production code in there. And it's very dangerous to do that. More often than not, you will not have that ability as a junior software engineer, or even mid-level software engineer, because it's just too risky to do. But as your application scales, your new features are added to your application, you might have to add new tables to it, or even add columns to already existing tables. So for example, in Facebook back in the day in like 04, I think I was on Facebook in 04. Like all you can do is like people's posts and comments, but as later on they migrated so you can actually like it, like all these different emojis, heart it, everything. So at some point, Facebook had to migrate or create a new table. Instead of just likes, it might have been impressions. And then instead of just liking, you can like heart it, like it, dislike it, thumbs up, thumbs down, laughy face, whatever the hell other impression you make on those posts. So they modified their database schema to accommodate those new features. So existing columns can be modified to hold new data types or new types of data, but just know schema modifications are generally scary to do, but you'll need to know how to do that. So changing database schema often isn't cheap. It can often require coordination with code changes and other tools, third-party analytics tool. Example, for this reason, take your time when designing your schema. I already mentioned that. You'll often be stuck your schema choices for some time. So think about domain edge cases and different directions your project might go to account for those changes. If you're convinced you wish you had a different schema, the time to make that change is now. Making the change will never be cheaper than today. So that's why make sure when designing your database schema, make sure you take your time. Single responsibility. So just like when you're writing code and functions and methods and classes, you want everything to be as small as possible. Same thing with database tables. Your table should only do one thing. So if your table stores students as well as addresses in the one table, you should probably split those up into two different tables, such as students and addresses, like so. So the same adage applies to storing data in the relational database. Large tables that store more than one record or model should be broken up into multiple smaller tables. So for example, here we have first name, last name, on probation, line 1, line 2, city, state, zip code. Where should this table might break off into two?
Starting with line 1.
Starting with line 1. So yep. So here we have the students table. Well, right here we have one big table, but it can be split off into two separate tables, a students table and an addresses table. But now we have to think about how do we associate Tiana to living at 381 Maple Street. So just like you wouldn't stand for repeating the same snippet of code. So if you, again, when you're writing code, if you're writing the same method or same little block of code over and over again, you might want to break that single thing off into a separate method and just use that method all over the place. So you're not repeating the same piece of code. Same thing, you shouldn't be repeating your tables or the data within your tables. So for example, if we have students and addresses, we have first name, last name, line 1, line 2, etc. And then we also have a students table with the student's first name and last name. So since we don't want to repeat the same data in different tables, because what if I happen to, say Tiana changes her name, I would have to change her name in the students table as well as change her name in the addresses table. And you don't want to be doing that. So what you want to do, and this is why this is a relational database, is there's duplicate code here. So what we can do in the addresses table is just remove the first name and last name and add a student underscore ID. So with this duplication, what are the downsides? We can expect if a student changes their name, we'd have to change these in 2 separate locations, and that can cause all kinds of errors. So what we want to do is add an address ID actually on the students table. So address underscore ID, and this address ID is associated with or related to the addresses table where the address ID is for. So this is where there's a relation between these 2 tables. And does anybody know why the address ID should go here and why we don't have a student underscore ID? So instead of having the address ID up here, maybe we have the student ID on the addresses table. Does anybody know why?
Each address could have more than one student, but each student can only have one address.
Exactly. Says because, what if Tiana has a sibling who also lives at 381 Maple Street? So Tiana has a sibling named Tom, and Tom also lives where at address ID equals 4. If students, go ahead.
Oh, I was gonna say, you might keep other addresses in your address database other than students as well.
Exactly, or a staff or anybody's address. Whereas if I had the student ID on addresses, that would only mean one ID can belong, one student can belong to an address. So there, if Tiana did have a sibling, there would be no way I can add them to this addresses table because Tiana already exists right here, where if it's that student underscore ID, like right here, and ID of 1, because Tiana lives at 381 Maple Street. If she had a sibling, I couldn't add like 1, 5 for another student. That's just not how databases work. You can only have one thing in the field or in each column at a time. And you can't store arrays in each field. You can't store objects. You can only store, integers, decimals, date, time, text field, etc. So this is how you would create this database schema.
So if there was a sibling, you'd create another column and that would be a different relationship. Like you could link 2 students together in a different column.
So it'd be like student 1, student 2, student 3.
Yeah.
So that's bad practice, because now what if, then you'd have to create your database to like the match edge case to have this, because technically what's saying that 1,000 people can't live at the same address? Let's just what's actually limiting that? So that means you'd have 1,000 columns to accommodate 1,000 different addresses or 1,000 different people. which is not practical. So you'd want to have the address field here, or the address column here, because here you can have 1,000 people living at address 4. Because if like Tom lived at address 4, I could be like Tom, Preet, on probation, probably true, and address 4. All right. Good schema design improves your data integrity. So careful use of database constraints such as column uniqueness or not null will protect you from situations like so. So the last line of defense on your data being stored in your database is constraints on what is allowed to be saved in your database, such as not null constraints, unique values, limiting how big a text or a var chart can be, and like just limiting certain values that can be put in there, such as here, email. I've got two of the same email addresses with 2 different passwords. If my database allowed for multiple people with the same email address to be saved, when James at example.com goes to log in and types in their password, like which user is it going to grab? So it might grab this one occasionally. It might grab this other one occasionally. So what we would need is a flag or a, when we're creating our tables, to have a uniqueness flag on this email when we're creating this table. So email must be unique. So if James at example.com already exists in this table, if another user, James at example.com, goes to create an account, it'll say, hey, that email is already taken, or this email already exists, or this user already has an account, select a different email. Or if you don't remember you having an account and you go ahead and create a new account, and it's like, hey, you've already created an account using this email, or someone has. Questions on constraints? And not null means, hey, if someone tries to save a user or save something in the database and there isn't a value that a user filled in for that specific field, it won't save the entire record. It'll say, hey, some value has to be in this field before it actually saves. Does anybody know what this password, why it looks like that?
It's hashed.
Yep. What does that mean?
Devin showed us all sorts of hashing last time, but it's just a way to, as an algorithm, you run across the password, and it's just, it makes it very difficult to convert it back to regular plain text.
Yep.
But if you have that hashing key or hashing algorithm, then it will convert it back into something usable.
You
Yep.
called it cell phone too.
Yep. Go ahead.
It
Someone
won't
else.
convert it backwards, just to be clear.
Yeah.
Hashing is a one-way function. So to check a hash, you actually have to reconvert. You have to recompute the hash and then compare the stored hash to the newly created hash.
Yep. So first, yeah, you never want to store passwords. What is it called? Store them.
Plain text.
Plain text. Yep. Yeah. In databases, because as we all know, companies get hacked all the time. Their data gets compromised. And if somebody has James at example.com and if this password is in plain text, they'd actually have that username's password, or that user's password. So you never want to store passwords in plain text. When we're doing with SQL right here, you're going to be storing passwords plain text. It's no big deal for just these examples, but don't worry, because a lot of frameworks and everything already hashes them for you and stores them hashed as well as salted as well. So they're nearly impossible to crack. What hashing algorithm is it? Not SHA-256, is it? Does anybody know the hashing algorithm?
AES 256.
Okay.
That's an encryption standard, but yeah, SHA-256
it is
is one
SHA.
of SHA is one of the hashing
Yeah,
algorithms.
okay. Yeah, those are, yeah. Okay. So yeah, which password should James check, or what password should the application check when James logs in? It can be either or. All right. So SQL queries, there are several commands. They're called queries. So select, insert, update, delete. So select, you'll retrieve any records that match a specific query. Insert, you're inserting new rows, new data into the SQL database or the Postgres database. Update, pretty self-explanatory. You're updating rows that match a specific query, and delete, you're deleting those rows. So just like we saw create table but in the back and earlier in the slides, we also have select, insert, update, delete. You'll be using select a lot, as well as probably insert the most, but more often than not select the most for querying. So by far the most common query is select, as I mentioned, allows you to retrieve data. So for example, a SQL query to grab all the students from the database would be select star from students with the semicolon. Don't forget that. You need that. So select star from students, you would retrieve all the students in the database. If you only wanted to grab the ID and first name, so select star, which is like for everything from students. If you only wanted to select the ID and first name, you would say select ID, comma, first name from the students table. And it would just grab the students and first name ID, or the first name and their ID. And you can add where clause as well. So often you want to retrieve only one record. So select ID and first name from students where the student ID. So ID equals 2. So that would be Elda. And you can do a bunch of other stuff. So with the where clause, there are numerous conditions supported by the where clause. So equals, such as where ID equals 2. You can do not equal to a value. So with the star, the not equals, or the 2 angle brackets. You can do greater than, less than, greater than, equal to, etc. You can write between, so between 2 values. So between IDs between 10 and 20, and between is inclusive. So between 10, that includes 10, and 20, that also includes 20. So in column is represented in a list of values, and like, so column matches a string with a wildcard. You'll see like occasionally, as well as I like. So instead of just like, it'll be like the letter I like. So if you want to match everyone that has a last name with the letter, or that starts with the letter R in it, you might use the like. So here are some examples. So let's select star from students. So select all the students from the students table where first name equals Andre. Select everything from the enrollments table where the grade is not an A. Select everything from the classes table where the credits are between 3 and 4. So we can use and as well, between 3 and 4. Select star from where grade is in A or B. And select everything from the classes where the name like starts with the letter art and credits are greater than 3. So you can chain these together as well. So these are this is more often than not, you'll be using the select to doing querying, to retrieving data from the database. If you need to insert records into the database, you do insert into students. So insert into the students table, and then parentheses followed by the row names. So first name, last name, birth date in parentheses. So these are like the column. I'm sorry, these are the column like headers. And then the values you want to insert in there are Michelle, DuPont, and then a date. And first name will always go to Michelle, last name will go to DuPont. So this also has to be in the order. The values need to be in the order of the columns as well. Questions about insert? Update is a little more involved. So updates allows you to bring changes to the value of a column. So for example, if I wanted to update a value in the addresses table, I'd say update the addresses table. I'll say, what do I want to set that value? So I want the line 1 to equal 200 Church Street, as well as the zip code to equal 600 or 60010. So these are the new values I want to set that record to. I'm saying where the ID equals 2. So I'm going to set whoever's user, the address where ID equals 2 to equal these column values. Delete, pretty standard. Delete from addresses where ID equals 2. Delete can be dangerous because if you don't add a where clause, you'll delete the entire table. So delete from addresses. If you just did delete from addresses, semicolon, it would delete the entire table. So always make sure you have a where clause in there.
Wouldn't that do that on the one previous to that too?
Oh yeah.
Pretty sure I changed everyone's first name to Diane one time.
Yep.
Because I didn't have where.
So here, this is exactly what it says. Caution. If you fail to include a where condition, you'll affect all rows in a table. So for example, is Everett just said, if you didn't have a where clause, it would set all the lines 1 and zip codes to these two values if I don't have a where clause. Same with the delete. All right. Any questions on SQL? All right. If nobody's any questions, let's go ahead and take a 10-minute break. Be back at 6:29, and we'll actually jump into actually writing some SQL in VS Code.